Well, good morning and thank you for being here. My name is Jorge Cano and I'm the head of research and development at Factum. It's a pleasure to speak today at the Georgian Museum of Art about our work with digital technology for cultural heritage preservation. In particular, the Selene Photometric Stereo System, or the Selene PSS that you can meet upstairs. I will also introduce the work we are doing at Factum Arte and how our collaboration within Archeox project is helping us document works of art with an extraordinary level of precision since 2022 that we started the Archeox project. Throughout this talk, I'll show examples of how these technologies reveal surface information that the human eye can't normally see, opening new possibilities for conservation, research, and storytelling. First, Factum Foundation is a non-profit organization based in Madrid dedicated to the digital preservation of cultural heritage. Our main goal is to use advanced recording technologies to document the surface of color of artworks, monuments, and objects in very high detail. This information is then used for conservation, study, and the creation of exact facsimiles. The foundation was established to ensure that digital technologies serve culture, not the other way around, helping museums, archives, and communities to safeguard their heritage. We work closely with Factum Arte, which is the cousin or the brother of the Factum Foundation. It's a workshops where artists and engineers work together, and while Factum Foundation focuses on research, documentation, and preservation, Factum Arte translates this data into physical form, combining technology with traditional artistic skills. At Factum, our work focuses on three main areas: recording, rematerialization, and dissemination. Recording is about capturing the surface and color of artworks in very high resolution using 3D scanners, photogrammetry, and systems like Selene. Rematerialization means turning that digital data back into a physical form through 3D printing, CNC milling, or other precise methods, always with artistic and conservation care. And finally, dissemination is about sharing this data for study, education, and public access. Together, these three processes create a complete cycle: recording, understanding, and sharing cultural heritage. The first step in our work is recording, and probably the most important part. It's capturing the surface and color of artworks and monuments in extremely high resolution. We always use non-contact recording technologies, which means we never touch or interfere with the object. These include 2D color recording, full 3D scanning, and what we call 2.5D, like the Selene, which focuses on the relief and texture of the surface. That means the topography of the surface. At Factum Foundation, we also develop new recording systems, adapting existing tools and creating our own solutions when commercial solutions don't meet the needs of cultural heritage conservation. As an example, this is a photographic manuscript scanner. It's a high-resolution, non-contact system developed specifically for fragile manuscripts and flat artworks. The scanner uses two cameras and a movable cradle that allows us to capture both pages and surfaces without touching them. This kind of tool reflects our approach, combining engineering, photography, and conservation to develop the right technology for each recording challenge. Another example, this system is called the Replica 360 Recto Verso, and it was developed for Italgas Heritage Lab in Italy. They have a huge photograph collection and they need to record it as fast as possible. So we designed this system with a turntable. There are two operators, one that plays the photographs on top of the surface and the other one that recovered it. There are two cameras pointing back from bottom and top, and using computer vision and software, it detects where the document is, and it triggers both camera and records at the same time. Here you can see the Veronica choreographic scanner. This is another system we developed. It's a photogrammetric one, and the system captures the surface geometry using a few lights and multiple cameras. You can see this arm. It has 9 cameras and 96 flashes. So it records in 4 seconds, 360 degrees, to reconstruct the 3D surface as busts and figures and small, let's say, small objects. It was originally designed for scanning fragile sculptures and has since been adapted for other uses in art and archaeology. The aim, as always, is to record with precision and care, creating digital models that can be used for conservation, research, and reproduction. One of the most famous systems we developed is the Lucida scanner, and it was designed by Manuel Franquelo and developed in-house to record the surface relief of paintings and low relief objects. The scanner uses a laser beam that moves across the surface, recording subtle variations down to microns, one more time without any physical contact. Lucida has been used around the world, from Egypt to the Vatican, helping conservationists and researchers see artworks, topography in incredible detail. This is the Selene Photometric Stereo System, one more time developed by us, in collaboration this time with the Bodleian Libraries as part of the Archeox project. We developed the system in 2022, and since then we've been recording part of their collection with it, getting really nice details from their collections. The Selene records the micro-relief of surfaces using a different technique. It uses multiple lights placed around a single high-resolution camera. Each light captures the way the surface reflects it, and allowing us to calculate its exact shape and texture. The result is a digital model with micron-level precision, showing every brushstroke, crack, or mark invisible to the naked eye. Compared with the Lucida scanner, Selene offers much higher resolution and sensitivity, so it's ideal for paintings, drawings, and delicate works on paper, like manuscripts, for example. The next step is the rematerialization. This is where we turn the digital data back into physical shape, creating exact replicas of or reconstructions for preservation, exhibition, accessibility, and research. Here you can see the facsimile of the Officiolo manuscript made for the Fondazione Giorgio Cini in Venice. It shows how digital data becomes a physical object again, matching the color, texture, and even the feel of the original, so it can be studied and displayed safely. This project shows the digital recording and rematerialization of the sepulchre of Cardinal Tavera in Toledo. The 3D model allowed us to study and reproduce the monument with extreme precision, preserving its form and surface for restoration and future generations. Here you can see the 3D reconstruction after recording. You can see every detail of the sculpture was digitally restored from the high-resolution data, revealing the original form with high accuracy. And here is the final texture model. The combination of 3D geometry and color creates a lifelike digital facsimile, preserving both the form and material qualities of the original monument. This shows the 3D printed head of the Cardenal Tavera, the transition from the digital model to a precise physical replica, ready for surface finishing and material testing. Here, one of our artists applies surface treatments to reproduce the marble's texture and tone, combining digital accuracy with traditional craftsmanship. And finally, several test heads showing different finishes. Each one helps us refine the color, transparency, and surface detail, ensuring the replica truly matches the original marble. The next 3 slides demonstrate the facsimile production process at Factum, from digital printing to hand finishing and large-scale assembly. Here, we are printing the color layers of a painting facsimile. Each layer is precisely aligned to reproduce the tone and surface of the original artwork with exceptional accuracy. After printing, the work is finished by hand. Artists carefully retouch and adjust every detail, ensuring the final result matches the original both visually and emotionally. This image shows the facsimile of the burial and glory of Saint Petronilla, a large collaborative project where our team worked at full scale, retouching the joints and unifying the surface to complete the final replica. Here we see the installation of the facsimile of Veronese wedding at Cana at the Fondazione Giorgio Cini in Venice. This large-scale project reunited the painting with its original location after centuries of absence. And this is the completed facsimile in place. It allows visitors to experience the artwork in its true architectural and cultural context. A perfect example of rematerialization serving both heritage and education. And finally, dissemination, making cultural heritage accessible both physically and digitally. Through exhibition, online platforms, and collaborations, we ensure that the data and facsimiles we create can be shared, studied, and enjoyed by everyone. Here we see the digital recording of Tutankhamun's tomb made available online. It lets anyone explore the walls in 3D and color. It's a perfect example of digital access to fragile heritage. This shows the Selene data published on the digital Bodleian platform. Each object can be examined online in extraordinary detail, supporting both research and public engagement. Later, I'm going to show you one of these online browsers if it would, controlling in real time the viewer. One of the important questions here within this online gallery is that we develop a tool that allows the user to relight the piece with a real torch. So you don't need to have the real object in front of you. This is the Politico Grifoni project, brought together dispersed panels from museums around the world. Factum Foundation created a digital and physical reconstruction, uniting the altarpiece for the first time in centuries. Here you can see the multi-layer viewer showing both color and 3D relief. It reveals the artist's technique and surface condition, tools designed for open study and collaboration. The facsimile was exhibited at Palazzo Pepoli in Bologna, allowing visitors to experience the complete work again. This is how digital and physical dissemination come together. And here's a replica of Michelangelo wax model installed at the V&A Museum in London. Dissemination also means sharing skills. So we train new generation through workshops and collaborations with universities and research institutions. In Naarden, the Netherlands, we led a hands-on workshop with Utrecht University students, teaching them 3D recording techniques, in this case photogrammetry. The students worked inside the Grotten Kerk, learning about photogrammetry and recording heritage in real conditions, combining theory and practice. So this project involves recording the whole space, and it was done by the students. We also organize online training sessions, sharing knowledge globally and making heritage documentation accessible to a wider community. To conclude, at Factum Foundation and Factum Arte, our mission is to ensure that technology serves culture, not the other way around. Through recording, rematerialization, and dissemination, we aim to preserve, understand, and serve cultural heritage with accuracy and care. And now I would like to focus on the Selene Photometric Stereo System. It's one of our most recent and innovative recording technologies at Factum. This system was developed within the Archeox project, a collaboration between Factum Foundation and the Bodleian Libraries, Oxford University. And Selene allows us to capture the microtopography of surfaces, revealing details at a level invisible to the human eye, and transforming the way we document and study works of arts and manuscripts. Again, this is the Selene Photometric Stereo System. It combines a single high-resolution camera with several controlled light sources around it. The Selene system is based on a technique called photometric stereo, and it involves taking multiple photographs of the same surface from a fixed position, each one illuminated from a different direction. By analyzing how the light interacts with the texture, the shadows, reflections, and highlights, we can calculate the surface orientations at every point, every pixel. So this method allows us to record extremely fine relief, often down to a few microns. Here we see the basic principle of photometric stereo. Several images are taken from the same viewpoint, each lit from a different direction. The shadows and highlights change, allowing the system to understand how light interacts with the surface, which gives us information about its shape. From those images, the software calculates 3 key outputs. The normal map, which describes the direction of every point on the surface. The albedo, showing the true color without shadows. And the depth map, revealing the microtopography with micron-level accuracy. Here is an example from the British Museum showing a cuneiform tablet recorded with the Selene. Each view, top, right, bottom, and left, capture how light behaves across the surface, highlighting even the smallest variations in the clay. And this comparison shows the results on the left, the color image, or the albedo, and on the right, a render of the 3D relief produced by Selene. The system reveals inscriptions and tool marks that are invisible under normal light, providing new data for research and conservation. The Archeox project, which stands for Analysis and Recording of Cultural Heritage in Oxford, is a collaboration between the Bodleian Libraries, the University of Oxford, and Factum Foundation, with the support of the Lady Hamlin Trust. The aim is to develop and apply advanced recording technologies to digitize some of the Bodleian's most valuable and fragile manuscripts with unprecedented detail. Here we can see the Selene system installed at the Bodleian Libraries in 2022. This is the first prototype. The setup allows us to record a wide range of manuscripts and objects. And this integration means the digitization process is both efficient and completely non-invasive. Now, here you can see a video of the first prototype working there. This is John Barrett, the one who is in charge of the system there in Oxford. And here you can see in fast forward how the system works. Basically, it can move freely in X and Y. It's controlled from the computer, and it triggers automatically the lighting sequence, and all the images goes to the computer, and then we can post-process them. Now let's go with some results. Through our 3D recording work with the Selene system, we've made several fascinating discoveries. Many features that are difficult or even impossible to capture through conventional photography are now visible for the first time. Here we see an 18th century printing copper plate from the Bodleian Library. The surface has darkened and corroded over time, making the design nearly invisible. With Selene, we can recover the engraved lines and textures that were hidden beneath that corrosion. When we look at the render of the surface without color or tone, the design becomes much clearer. You can think of this render like a digital plaster cast of the surface, one that can be virtually relied from any direction, allowing us to study every engraving and imperfection. Selene doesn't just capture color or create visual renders. The data it records allows us to make precise surface measurements and comparisons, and to document entire originals, not just small areas. And what's particularly important is that the processing, viewing, and storage of Selene's 3D data require far less computing power than earlier high-resolution scanning methods. This is the reverse side of the same copper plate. The surface appears plain at first, but once processed through Selene, a completely different story begins to emerge. Here's the 3D render. It reveals something extraordinary, a piece of engraved music hidden on the back of the plate. These fine incisions were almost invisible before, but the microtopography data brings them back to life. Here's the 3D render. So, a piece of engraved music hidden. By reintroducing some of the original color information, we can overlay and annotate the markings, helping researchers to read, analyze, and interpret the plate in context. Now, for the first time, we can clearly see every note and every word, information that had been hidden for centuries. This demonstrates how 3D recording opens entirely new possibilities for research and conservation. So we can capture color and make renders of the surface, but the data which the Selene captures allows us to do even more. We can also take detailed measurements, as we have seen in the previous video. We can record large originals in their entirety, not just small samples. Processing, viewing, and storing these 3D recordings is easier than before. In this particular case, the reverse side of the copper plate was reused as a practice surface, a space where engravers refine their technique and experiment with lines and compositions. In fact, there is a researcher that proposed that all these marks belongs to William Blake, with 14 years old. Moving on, the Bodleian's Japanese prints and manuscripts are among the most colorful and visually rich works in their collection. Here we have an example of one of their woodblock prints. The impression left by the woodblock on the paper has been captured by Selene. Every ridge and depression can be analyzed in detail. Looking closer at this 3D render, we can appreciate the surface texture. These recordings reveal that Japanese prints were never purely two-dimensional. Artists and printers deliberately used textural elements to enrich the surface. Thanks to Archeox and Selene, we can appreciate these works as truly three-dimensional creations. This is one of the largest originals recorded so far with the Selene system at the Bodleian libraries. It's a nearly map containing an extraordinary level of hand-drawn detail. The recording reveals the pinholes used in the copying process, small perforations made to transfer parts of the design from one sheet to another. These physical traces, almost invisible to the eye, tell us a great deal about the techniques and working methods of the map makers. Dating to the 14th century, the Gov map is one of the earliest maps to show red writing in a geographically recognizable form. This is the render of the 3D surface of the map, captured at over 700,000 pixels per square inch. And in order to capture the map at that resolution, it was necessary to record the map as 85 image tiles, which were then stitched together. This is the highest resolution recording of the map to date, allowing researchers to zoom in to specific areas of interest. When we look at the render of the surface, we can see groupings of tiny pinholes. These holes are evidence that the position of geographical features were transferred to the Gov map from an earlier map or precursor map. Those are the pinholes. And the new 3D recording has been used to produce a double-sided, one-to-one, three-dimensional facsimile of the original. So it can be used for study it without touching the original. From this point, I'll show you a series of images, different types of surfaces, and projects recorded with the Selene system. The idea is not to go into technical detail, but to give you a sense of for the range of materials and scales we can work with. In this case, this is a seal. Some fossils can be also recorded using the Selene. The system was designed with almost flat surfaces in mind, but as you can see, you can also use it with objects with more depth. This is a butterfly specimen. Oh, sorry. Let's skip this video. This is another example of the type of viewers you can create from the Selene data. It's a multi-layer viewer. You can see you can drag and drop the different layers, switch on and off, and obviously zoom in and out, exploring the data. But the most important part is this tool. It allows you to change the material quality of the object, like the metalness or the depth. Increase the contrast and relight, moving the virtual torch. And this is an online tool, so you don't need a specialized software, just the browser. This is another example. This is a seal from the 13th century, if I am correct. The viewer is Tupolev compatible and is based on Mirador viewers. And I'm going to finish the presentation talking about the Selene circle. These are some of the institutions currently working with the Selene system, what we call the Selene circle. From the Bodleian Libraries to the British Museum, Princeton, and even here at the Georgia Museum of Art, it's a growing network of organizations using the technology to explore and preserve cultural heritage in new ways. The Selene circle is a place to share experiences, to develop even more the technology, and the main goal is to share what we are doing with the system. And I'm glad that Georgia Art Museum is joining. This is the end of the presentation. So. I don't know if you have any questions or doubts. Well, we work mostly with the imaging departments as we prepare the tools for them, and then they are the ones that work with the conservators. In Factum, we have our own conservation team, but yeah, mostly with institutions, we work directly with the imaging department. Yeah. I can reply to your question later. I have to read again the project. We work in a. I mean, we can work on dozens of projects per month, and I don't have all the details in my mind. Sorry. Yeah.
In this example, it seems like you're working with stable light source. Is it possible to combine Selene with more practical images as well?
Absolutely. Yeah. I mean, what we do with the Selene is kind of creation of a map. And in mapping with geographical information system, you work a lot with multi-layer information, and this is the same. The more data you have, the better. You can start working with machine learning, different processes. So yeah, it's completely compatible. It's just another layer of information. The outputs of the Selene are images, are TIFF images, and they are, let's say, scale. So you can measure on top of them. So if you have another layer, let's say an infrared image, you can place it on top of it and just layer them. Yeah. Sorry, could you?
Mentioned that the depth information with nanometers, because one would curious how this system works, what they need.
Yeah, the camera is a 47 megapixels camera. We are shooting at 42 more or less centimeters. So the resolution we have is 1100, more or less. So that means that each pixel measures in the real size of each pixel. It's about around 25 microns. So this is the resolution in X and Y, the average resolution. And we are able to measure around 25 microns in X, Y, and Z. I'm not sure if that is your question is clear now, or?
I mean, it seems easy to achieve high resolution, but for you, it's a deep the depth information that you mentioned seems, what's unique about this system?
About the Selene system? Well, there are a couple of things unique. If we compare with photogrammetry, we have much more resolution here. If we compare with the Lucida scanner, which is a laser triangulation one, you project a laser line, you move it, and you record the shape of the laser line on top of the surface. For example, in that case, you will get only the 3D data. With the Selene, you have the 3D data and color information at the same time, and perfectly aligned. So you don't need a post-process to align both data in the same coordinate system. So these two things, I think, makes the Selene unique. Also, the recording is quite fast. It's just a pop, 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 pop. It's like 6 seconds or something like that to record one tile. So this is something meaningful, let's say, in cultural heritage, because the faster, the better. So there are a few things. I mean, we designed the system with all these questions in mind. The truth is that at the very beginning, when we started the Archeox project, the goal was to record copper plates and palm leaves manuscripts and manuscripts. And we ran a few tests, and we realized that our system didn't have enough resolution. So we tried a commercial unit. It was a profilometer. It's using scientific work and so on. It can record with microns. I mean, less than 5 microns, something like that, between 5 and 50. I don't remember the exact details. The cost was $400,000 for the machine. The time it takes to record this area was minutes. So we decided, hey, we have this technique, let's try with it. We realized that it's more than enough, was more than enough, and we go for it. So this is the typical way we develop technology. If we can find something in a commercial, like a commercial solution, or the commercial solution doesn't fit the need, we create something. I mean, based on, I mean, we use different pieces. For example, in this case, we use a Canon camera. We are not developing a new camera, but we integrate the different pieces together and create the software and so on. So this is why I think this system is unique, because we design it in a very specific way with a very specific need in mind. Not yet.